Hello everyone, this is Christian Worm again on my series of videos in different topics in solid-state physics and semiconductor physics. Today we're going to be talking about density of states in a crystal or semiconductor crystal and what that's all about and how we derive that in 3D, and we're going to look at deriving density of states in two-dimensional too, which is very interesting and has some pretty cool applications. So up to now you should be familiar with the two things you see on the board right here. This is the energy momentum plot for an electron in some crystal, and we can each of these bands represents a eigenvalue, which is your energy, and separated by this band gap Eg, which is 2 times the absolute value of V sub n, and V sub n is your your Fourier coefficient for potential energy for the nearly free electron model, which we will maybe go into in another talk. But I also have the time-independent Schrodinger equation up here for one dimension. Phi is the wave function, V is our potential, E is going to be the electron energy. And so what we're looking for in density of states is we're looking for how many, where are the states available for an electron to exist in some band in a semiconductor. And we know from this that electrons can only exist in these bands and cannot exist in between in this band gap region, and so if electrons exist on these bands from here to here, what we want to find out is how many electrons can we get on some on these bands per unit energy. So how many electrons can I fit in this delta E region, right? And what we're going to do is we're going to find an available state in the real space, transfer it to, find it in K space per unit volume. We're going to find it in terms of K. We're going to use the Schrodinger equation. We're going to get the free electron energy model, and we're going to write this density of states in terms of energy right here, because that's something we can measure. We can't necessarily measure K. Remember, K is the reciprocal space there, and you can kind of think of it as, if you're an electrical engineer, you can think of it as going from the time domain to the frequency domain. So K is kind of like it's kind of the frequency domain. If that's how you think of it, it's not very intuitive to understand, but we're going to get right into it here. Let's look at the real space. In real space, we have an x, y, z axis, and we have a volume, with sides A, B, C. And so volume in real space is equal to A, B, C. Okay, but mathematically, the real space really doesn't do a whole lot for us when we're analyzing semiconductors, and that's why we need to go into the reciprocal space, which is simply, it's going to give us, and this is just some arbitrary volume then. Well, it's not arbitrary because we know that the state, an available state for an electron is in some volume. We don't know what it is, but it's just some volume, and we're going to call it, pi over B and pi over C, right? So that's one state per unit volume. I'm going to extend this out a little bit because we're going to need this more. So, okay, this is y, kx. I can go ahead and erase this right here. And kz. So you should be familiar with this, how to transfer from a real lattice to a reciprocal lattice. So yeah, we have some, we know that one state is in some volume pi to the 3 A, B, C. And we can rewrite that as rho, and let's call it rho for now, is equal to ABC, which is just V over pi to the 3. But wait a minute, one state can hold 2 electrons because electrons are fermions. Fermions basically have a spin up and a spin down. You should remember this from chemistry right here. here's one state can hold 2 electrons. That could be like a 1s orbital in some molecule, right? And so I can actually multiply this by 2. So that's 2 electrons per state. And well, I have 1, 2, 3, 4. I have these 8 lattice points, right? And each of these points is only 1/8 of a full lattice point in a reciprocal space. So that's going to change rho to V over 4 pi 3. So this is the states per unit volume in K space. Okay, so let's go back to K space again, and we want to find this in terms of K, because we find it in terms of K, we can use the Schrodinger equation, or we can find the nearly free electron energy, and we can find K in terms of E. So I'm just going to rewrite this, make it look a little bit better. Remember, this V, I already said this V is in real space, so we're going to look at this right here. So again, this is Kx, Ky, Kz. Okay, and then our box is in here, looks like this, that's our volume box. And we're going to look at 2 spheres in K space. Well, it's actually 1/8 of the sphere here. And what we're doing is, this distance here is going to be delta K. This radius is K plus delta K. And this radius here is just K, right? And we want to find the states inside this differential distance between these two spheres. And the volume of that differential space is just, I'll call this V sub K, is equal to the surface area, which is 4 pi K squared, times the differential spacing, which is just D sub K, right? And I multiply these two together, and I get number of states in this K space. And so that's going to be equal to, we'll call this rho sub K. I think actually we call it N. This is a better term. So N is equal to V over 4 pi 3 times 4 pi K squared delta K. Okay, cool. All right, well, that's going to cancel out. That's going to cancel out. And I can rewrite this as V K squared delta K over pi squared. Okay, so that's my states per unit volume. Number of states in some volume in K space. Actually, now it's just number of states, because we multiplied this volume by this differential volume here. So now we just have states. We don't have states in terms of K. But okay, so I'm gonna erase some of this, and I'm gonna rewrite N here over pi squared K squared delta K. Okay. So you probably already know, free electron energy is equal to K squared H bar squared over 2m. And just to kind of review where that comes from, in a semiconductor crystal, obviously we do have some potential that's resulting from each atom, that it's going past in the crystal, and it looks something like this. And this is like the, kind of like the Croning penny model here. Here's each atom, each point, and inside here, we have a conduction band and a valence band, a conduction band, valence band, and in K space that would be, this band right here. So our electrons, they're only mobile in the conduction band, which is up here and higher, right? So if your electron's up here, it's moving without relatively no interaction at all from the potential given off by these lattice points, right? we use the nearly free electron model to show that isn't necessarily so. But in this case, for this derivation, we can assume that there is no potential energy from the lattice acting on each electron. So that means that that this term right here, the V, so my potential just goes to 0, and I rewrite this equation into a second order ordinary differential equation we can solve. Which is d squared phi of x over dx squared plus k squared phi of x equals 0, right? Just like that. And what is our k squared? K squared is equal to 2m, e mass of the particle, electron in this case, over h bar squared, right? And that is how we get our free electron energy right there. Yeah. So the k is the coefficient that's used in this ODE, second order ODE. So let's go back to that. Just wanted to kind of mention that real quick. It's not super important. We want to find k squared and delta k in terms of e, right? Because e is what we can measure. E is what where a lot of our math is going to come from, right? So, well, I can say k squared. So right, so here k squared is equal to 2me over h bar squared. And kind of our side note. If I take the derivative on each side, I get dE is equal to k h bar squared dk over m, right? Well, dk is delta k, right? So let's write this in terms of dk, right? dk delta k is equal to dk, which is equal to m dE over h bar squared times k. Well, k is equal to 2me, again this is from this right here, over h bar squared. So I'm going to rewrite this equation right here, and I'm going to get something n in terms of energy is equal to, first I'm going to start with v over pi squared, right? K squared, well that's this right here, right? 2me over h bar squared, right? Times dk, that's this guy right here, mdE, mdE over h bar squared, right? And k, 1 over k, that's going to be h bar squared. Oh, I'm sorry, this is I made a mistake. This is just h bar, right? That's just h bar. Yeah, because I square rooted, both sides here. So 2me. Okay. Just make sure I'm on the right track here. I'm going to simplify this. Okay. I'm going to erase this stuff. When I simplify this n of e, then what we get is v over pi squared n 2m dE over h bar 3. Let's double check here. This goes up here, cancel, cancel. M square root of m. Okay. Can bring that out, or we could bring m out and write m as in terms of 3 over 2. And now I have the number of states, right? But I want to find the number of states between E and DE, right? So between DE, we want G of G density of states in terms of dE. So that's going to be NE over volume times this dE, right? Per volume per energy. Well, that just becomes, right, this, and we're going to rewrite M as M star because in the semiconductor crystal we have effective density, effective mass, which can change depending on where you're at in this band right here. So we're going to call this M star to the 3 over 2, right? 2E over H bar 3 pi squared. See how we're going to, yeah, okay. That's density of states in 2 dimension. But if we're just considering the conduction band, everything from this here and above, right? We take this is referenced as our conduction band, this is referenced as our valence band. Then we want to rewrite this actually as Mn star to the 3 over 2 root 2 times E minus EC over pi squared H bar 3. And if you've taken any general semiconductor classes, this should look familiar. So just should look very familiar. So this is the number of states per energy per volume in real space. So that's how many states we have somewhere in here. And similarly, so this is how many available states there are for electrons. And what's important about this is this tells us how high we can dope a semiconductor. If we want it to be N-type, we want to how highly N-type can we make it? If this is a large number, that means there's a lot of available states for us to make it more N-type, more free. We can dope it with more free electrons. And you'll find a big reason silicon is used so much in microelectronics is because this number is fairly high for both the conduction band and the valence band, for holes in the valence band and electrons in the conduction band. And they're both fairly equal, which is what makes it great for CMOS. So similarly, our density of states in the valence band, you can guess that's going to be M star P. That's your whole effective mass. We'll write this a little bit lower. M star P to the 3 over 2, now it's EV minus E over pi squared H bar 3. I'm not sure if you can see all that, but that's it right here. So if we're looking, let me rewrite this real quick. Conduction band, valence band. If this is E, and this is EC, if we want to find the available density of states, in here, it's going to be E minus EC. If we want to find the available states between here and here, this is EV, it's going to be EV minus this E. And that's this energy right here corresponds to this term. And this energy difference right here corresponds to this term. And that's how we find that. So, okay, you see that? I'm going to explain one more thing, and then I'm going to go on to two-dimensional density of states, or density of states in 2D. Just to reiterate on this, when we're looking at carriers, the number of carriers in an electron, we're actually, that's N equal to intrinsic carriers, bottom of the conduction band to infinity of rho sub E F of E dE, right? And this is actually where we get the effective density of states. The effective density of states is the number of states available in the conduction band. Because in real life, generally when we dope something, we dope a semiconductor with make an N-type, the electrons they're not gonna go up here, here, here. They're gonna go within this area about 3 kT above the conduction band, right? And if you see F of E, I believe, looks something like this, right? Make it a little more narrow, something like this, right? And here's, conduction band, right? And this is like, 3 kT conduction band. Right? So this is where most of our carriers are, just within 3 kT. And that's where we get, the effective density of state is from this integral right here. Okay, so let's talk about two-dimensional density of states, and we'll talk about why that's important. So let's look at some two-dimensional crystal. It has sides A and B. So it has some area in real space, A and B. Okay, but how about reciprocal space? Right, that's where that's where we're doing all our math in. Just gonna write this. Right, it's pi over A, pi over B. And we can say that the number of states per unit area in reciprocal space is simply A over pi squared, right? Well, we have 4 points, four reciprocal lattice points, and it's a fermion, spin up, spin down, 2. So that changes number of states in some area in K space to A over pi squared 2, right? And again, let's rewrite K space. Here's our area. Here's our area that we're talking about up here in K space, and Kx, Ky. Okay? We have 2 circles, separated by some dk with some radius k and some radius k plus dk, right? This area between these two, right? We want to cancel out area and just get the number of states is equal to this A over pi squared 2 times, what's the circumference of the circle? That's 2 pi r, which is k, times delta k. Get that right there? Double check that. Yeah, that's right. Okay. So, can rewrite that as A k dk over pi. Okay. Let's go back to free electron energy. What do we know from free electron energy? E is equal to k squared h bar squared over 2m, right? K is equal to 2m e over h bar, right? And dk is equal to, I'm going to write that, dE is equal to k h bar squared dk over m, right? So dk is equal to m dE over h bar squared, right? My dk, and I have dk here. I have, k. Get that. So I can rewrite that as m dE over 2me 2me h bar squared, h, that cancels out. And plug that into here. Now we want to write this in terms of E. So you write A over pi, K, 2me over h. I'm sorry, h bar, right? That's Planck's constant. I probably should have mentioned that earlier, but you should know that if you're watching this video by now. dk, which is mbe over h bar 2me. Take a look at that. And what's interesting about this? Let's rewrite it. N of E is equal to, A over pi MBE over h bar squared. So really, N of E, in terms of energy, is just constant, right? It's completely independent of energy, right? Well, we have this delta E right here, but when we transfer this to, call this 2D, then area and dE go away, and we just get something that's in terms of m star over pi h bar squared. So if we plotted it, it'd just be constant. So as we go higher and higher in density, higher in energy from the conduction band, we're going to have the same amount of available states everywhere, and it's going to correspond to this. It's true because m star is a function of energy. It will it will change a little bit, but in general we have a lot more states as we go higher up, as opposed to density of states. That's Fermi, as opposed to density of states in 3D, in which case it decays like this as we go up in energy. Right? It saturates. Right? So that's pretty interesting. What's an application like that you would see a 2D density of states? You'd see it in 2D materials such as graphene, or MOS2 is another popular one that's being used in semiconductors right now. And aside from that, we also see it inside quantum wells in compound semiconductor heterostructures. When you see something like this, right? If this is gas and gas, gallium arsenide, aluminum gallium arsenide, dope it to Fermi levels here. Well, in this region right here, your electrons, they act as 2D electron gas, and so in this space right here you have a two-dimensional density of state. So here you have very high mobility and a lot of other really cool characteristics, in EC. So that's it for density of states. I will be doing some other videos on carrier statistics and Boltzmann-Maxwellian equations in semiconductor